Well, you may have seen my video already on the position time graphs, and now I'm going to look at the other kind of kinematics graph that we often make for one-dimensional motion, and that is a velocity time graph. So I'm going to reinforce what I said on that last one. This is looking at one-dimensional motion. This is a train on a track. This is a little physics lab cart on a track, not something that's going in 2 dimensions, even though sometimes it looks on a graph you've got an X and a Y. This is not an XY graph like grid paper. This is velocity versus time. Okay, and so I've shown pretty much every kind of motion that you'll typically see on this particular graph. I've got 7 different segments. I'm just going to describe each of them and show you how to pick out what kind of motion you're looking at. So in segment A, notice here that it's a horizontal line. And any horizontal line means something's not changing. In this case, the velocity is not changing. Doesn't mean we're not moving. This is like cruise control in your car. It just means you're not changing your velocity. And the other feature we want to look at is what direction are you going. Now, because this is 0 on the velocity time graph, anything above that 0 is positive, or we often call it in kinematics just the forwards direction. So segment A indicates something moving forwards at a steady speed, or I'll just use the word constant. And those are the 2 features we want to look at, what direction and what's happening to its motion, if anything. And then segment B, notice we're still above that 0 velocity line, so that's still forward motion, but we're now changing speed. And how are you changing the speed? Well, it's approaching that 0 line. 0 would be no motion at all. So this must be a case where we are slowing. Now be careful. Don't think everything downward is always slowing, as I'll show you in just a moment. What's happening here in C? Well, the velocity graph is staying right at v equals 0. So you might just call that stopped for a moment. And then in segment D, I warned you not to think of any downward graph as getting slower, because now we obviously can't get any slower than being stopped. We're going to be getting faster, but what's different is we're starting to move backwards now when we get into this negative region of the velocity graph. So this is backwards. That often in horizontal motion would be looking like leftwards. If this were vertical motion, this might be downwards. It just depends on the orientation of your particular motion. And it's getting faster. So just watch out for that v equals 0 line. That's a great reference line, because everything getting farther away from that must be getting farther away from being stopped. And that, when I say farther away, not in space, but in terms of its speed. So it must be getting faster. And then in E here, we're again at a steady speed because it's flat, but this is now backwards and steady. And then segment F, still backwards. Again, don't be fooled in thinking heading up on the graph will mean moving forwards, because as long as you're below this time axis here, that's got to be getting backwards. So we're moving backwards still, but we're approaching the no motion line. So this is also slowing. So notice that segment F, similar to segment B in that they're both approaching that time axis, and they're both getting slower. Very different than interpreting a position graph, and that's what people tend to get confused. They want to think like, oh, I was looking at a position graph a moment ago, so I'll just keep interpreting it that way. And that's probably the most common mistake I see my students make. And then what's going on in G? Well, G is back into the forward motion part. But now, because we were to stop just a moment ago, we must not be stopped anymore, and so it's getting faster. And I drew G a little differently, just so I could show you the difference between getting faster, like G is getting faster, and then what's going on down here in D. Now D obviously is moving backwards instead of forwards, but the other thing I want you to see is that the slope of D is more slopey, as I often say, more slopey than what you have here in G. And what's important on these graphs is that the slope is equal to the acceleration, the rate at which you change velocity. So while both are getting faster, G is getting faster with less acceleration. So it's just going to take longer to change its speed. So slope equals acceleration, and as you can see there, 5 of those segments have different slopes. I'm sorry, 4 of them, B, D, F, and G. And I drew B, D, and F with similar slopes, and then G I tried to make noticeably different. So those are probably the main features of velocity time graphs. I do want to show you one more thing, and I think I'm going to pick a different color here to draw this in. Now, I'm not going to do anything quantitative with this. I'm just going to show you a description of what we're doing. So there's a feature that some people have never seen this done before on a graph. But if we shade in the area, let's shade in the area defined by segment A. And when I say the area, I'm talking about the area bounded by the graph itself, that's the green part, and the time axis, that's my horizontal axis, and then all the space in between there. Now, that little shaded area can be measured, just like you measure any area, base times height in this case, but what we're going to use for the height is actually velocity measurement up here at A, and the base would be how much time that is. And what we're finding there, when we find that area, is the displacement that occurs during that particular segment. Displacement is how far you end up moving from where you started in that segment. So that would be some number with a unit like meters or kilometers. And then notice here, even though B begins with the same velocity that A ended with, because we're getting slower the whole time, we don't end up moving as far. In fact, for a similar amount of time, we would move half as far, because that little triangle there has about half the area that the square did next to it. Now, if we get down below the graph here, it's done just the same, except now your time axis boundary is up above, and your graph is down below. And so for segment D, the displacement would be found by calculating that area of the triangle. And similarly for any of these segments here, E and F, and then G, G might have as much displacement, but notice it's because it took a longer time to change that speed. And so all of those segments there, if we were to add up all of those areas, we would get the total or net displacement during the entire time interval shown on the graph. So another thing that's real commonly done with velocity time graphs. So I'm going to end that here. Hopefully now, between the position time graphs and the velocity time graphs, you've seen just about everything that we can do with kinematics graphs.